Hey, good morning, everyone. So I'll do a brief recap of the AC analysis, chapter 5 material that we have covered in the last class, and then we'll proceed to the examples. Okay. So, all right. Now, AC analysis deals with circuits comprising of resistors, capacitors, and inductors. The only difference between a AC circuit and a DC circuit is basically the source. So the source is a alternating current generator, AC function generator, versus a DC power supply. So both can be called as power supplies, except one supplies a constant voltage and constant current, so it's DC, and the other one is AC. The components are the same: resistors, inductors, and capacitors. Those are the only three components we study in this course. Those three components are also the foundational building blocks of all circuits. Resistors behave the same way for AC as they do for DC. Inductors and capacitors are energy storage devices, so they function a little bit differently. When it comes to AC voltages and currents applied to an inductor and capacitor, because they're energy storage devices, energy flows into the components and out of the components constantly. And depending on the frequency is basically how many times a second the AC input is switching between a positive and a negative value. And so when it's positive value, it's going into the energy flows into the components. The other half cycle, the energy flows out. So depending on the frequency, meaning how high or low the frequency is, this energy transfer takes place at a higher rate or a lower rate. And since the voltages and current equations for inductor and capacitor are time dependent, again, that's due to the rate of energy transfer, right? Energy cannot be transferred in an instant, so it takes a finite amount of time. So the voltages and currents always have a dependency on time. So if you wish to analyze an AC circuit and we wish to find the voltage and current for a capacitor or an inductor, we have to write out differential equations. And again, if you have not heard me say it before, differential equations are not my idea of a good time. I mean, there are some people who enjoy doing the math. I'm not one of them. Thankfully, greater minds that have come before us devised a unique method. Well, unique in the sense that applied to solving these equations. And they figured out if we represent some of the quantities with the imaginary number, meaning if we use complex number math, we can reduce these differential equations to simple circuit analysis problems. And when I say simple circuit analysis, I mean the techniques that we studied in chapters 1 and 2. Okay, so we replace sources with something known as phasors, and inductors and capacitors with their impedances. Both phasors and impedances are complex quantities represented with the imaginary number. The imaginary number I is noted by J in electrical engineering because I is used for current. So that's the brief recap. And I'll take a pause. Let me know if you have any questions thus far about anything. Yeah, any questions from anyone? Okay. So before we get into the example problem, again, want to point out the rectangular and polar coordinate conversion. Because there are complex quantities, we represent phasors and impedances using a vector. A vector needs two things to describe it: magnitude and direction. Magnitude is given by the length of the vector, and the direction is the angle that it makes with the real axis. Now, if you have a programmable calculator, you can program equations in any coordinates and it will give you an output directly in one step. If you don't have a programmable calculator like me, then I do math using the equations from here. Even that can be simplified because most engineering or scientific calculators are able to perform a direct conversion between polar and rectangular to polar coordinates. So conversion on a calculator. The reason we convert polar to rectangular and rectangular to polar is because the math operations, it's easier to perform summation, addition, and subtraction if both numbers are in rectangular coordinates. It is easier to perform multiplication and division if both numbers or multiple numbers are in polar coordinates. And I will show you how and why. So let's say you have two complex numbers and both are in rectangular coordinates. A plus or minus JB, and you're either adding or subtracting another number, which is C plus or minus JD. So you have a real component, which is A and C, and you have imaginary components, B and D. And again, keep in mind, the real and imaginary simply refers to the mathematical notation. Okay, simply refers to the mathematical notation. Imaginary does not mean it is a figment of somebody's imagination. They have a real basis. I mean, they have a physical basis in real life. Okay. And again, that's why we have, prereqs for the classes. Hopefully students have learned about this in the prereq math classes. But anyway, to add or subtract two imaginary numbers, you would simply take the real the real portion of the numbers and add or subtract them together. And you would take the imaginary portion and perform the operation on those respectively. Okay, so again, it is easier to perform addition and subtraction of two or more complex numbers if they are all in rectangular coordinates. You simply take all the real portions together and you take all the imaginary portions together. Okay, let's take a pause. Let me know if you have any questions about this. So far, so good? Okay. All right, then multiplication and division. Let's take it one at a time. If you have two numbers, and you're trying to multiply them together, let's say magnitude of A with a phase angle of B, trying to multiply this number with another one that has magnitude C and phase angle D. Anyone know how to do this? It's similar to the addition subtraction. So you would take, yes. Yes, so we would multiply the magnitudes together. We multiply the magnitudes together. And if you think about the graphical illustration, it's a right angle triangle, right? It's a right angle triangle. So if you take two individual vectors and you're trying to multiply them, what multiplication itself is a shortcut for addition, right? 2 times 2 means you're adding 2 twice. 2 times 3 means you're adding 2 3 times. So magnitudes of these vectors get multiplied. You're adding them that number of times. But the phase angles are not multiplied. The phase angles are added up. So magnitude A times magnitude of C, with the phase angle B is summed up with phase angle of D. Okay. Make sense? Okay. And then division, similar, but if you have 2 numbers in polar coordinates, the magnitudes are divided. So magnitude of A divided by magnitude of C, the phase angles are subtracted. It is numerator minus the denominator. Numerator minus the denominator. All right, let's take a pause. Let me know if you have any questions. Any questions from anyone? Okay. And of course, this is not electrical engineering. This is from math. Math applies to all areas and all fields in our world. So even in your own field, it doesn't matter what field of engineering or scientific field you may be from, there will be a time where you would encounter complex numbers in your own field of study. So this, I think this is an important slide for all engineers to understand, okay? Again, it's trigonometric identities because the vector forms a right angle triangle, and then conversion from one coordinate system to the other one is based on trigonometry. Now, these calculations, again, there are many tools that can directly perform this, okay? My calculator is from the 90s, 1992 to be precise, more than 30 years old. So it's not programmable, okay? It can, however, do a polar to rectangular and rectangular to polar conversion, okay? But it cannot directly give me an output for this kind of equation. Your modern programmable calculators can, okay? Your modern programmable calculators can give you this output. The only thing is the equation would be long, so you need to be an expert at programming your own calculator devices to program. This is just one part of the equation, because we are talking about the purpose of these equations is, let's say we apply to Ohm's law. If you apply to Ohm's law, voltage is equal to current times resistance. In this case, it would be current times impedance. So you're performing a multiplication. And since both current, impedance, and voltage are in complex number math, you are multiplying 2 complex numbers together. And that is how we are going to use these equations. That is how we are going to use this math. So if you are multiplying 2 complex numbers, or perhaps you're dividing 2 complex numbers, you can simply program that entire equation into your calculator and get the answer in one step. Does that make sense to everyone? But if you make even a slight error in programming that equation, instead of a plus or a minus, you might enter like a, change the sign perhaps. You might neglect to enter it in degrees, perhaps at radians, and then you end up with the incorrect answer. Okay. And when we go into examples, I would recommend students take out their calculators and go along solving as I go along. Okay. So let's take a 10-second pause before we get to the examples. Let me know if you have any questions. Any questions from anyone? Okay. All right, so let's look at examples 1 and 2. Examples 1 and 2 deal with phasors, meaning you are taking the source and how can we combine two or more sources together. So again, we don't know anything about the circuit. We don't know anything. This is simply an example or two examples to show you how you can deal with sources in an AC circuit. So it's mostly about math. Okay. And then examples 3 and 4, again, there are no circuits, but we're going to use Ohm's law and see how we apply it to inductors and capacitors. So that's example 3 and 4. And then example 5, we put all of it together to apply it to one large circuit. Okay. So examples 1 and 2 deal with sources. Examples 3 and 4 deal with inductors and capacitors. And then example 5, we combine everything together. Okay, so Vs of t, example 1, Vs of t is given as 10 cos omega t plus 10 sine omega t. Okay. We are asked to find what is the value of this summation or this addition. Okay, what is the value of Vs of t? Now, the first thing I like to point out, first thing, again, it's a concept, it's not the math, is that in order to add two or more signals together, their frequencies must be the same. This is the most important point at the beginning, at the top, okay? In order to add or subtract, and I'm going to write this down. Add or subtract two or more signals, sources, waveforms, functions, all synonyms in this case. Their frequencies must be the same. If it's not, we cannot, if they are not the same, we cannot add or subtract them. Okay. We simply enter it as a equation, meaning x plus y minus z. That's it. We don't do anything to it. So a real life example of this would be your noise cancellation technology. Okay. Every phone has noise cancellation. Okay. Noise cancellation works on the principle of taking a microphone, placing it near your speakers. And as an example, let me just draw out a simple circuit right here. So let's say the microphone captures a signal like this. It is this captured signal from the microphone is then passed through a circuit that changes its phase. That changes its phase, meaning 180 degrees out of phase. Okay, so this is 180 degrees out of phase. Out of phase here indicates just the phase difference between the two. And you add it together, the result is 0. Okay, that's the basic principle of noise canceling technology. Every phone, even going back to the days of flip phones, not just smartphones, there used to be like a small microphone next to the ear. And so, sorry, the ear speaker. And so the microphone would capture the surrounding sounds, pass it through a circuit, immediately flip it 180 degrees out of phase and add it to that incoming signal. So then the signal does not interfere with the output that's coming from your speaker. Again, all noise canceling headphones, earphones technologies use this exact same principle. So when you add two waveforms together with the exact same frequency, exact same amplitude, exact same magnitude and values, but they are 180 degrees out of phase, the resulting output is equal to 0. If it's not the same frequency, you cannot add or subtract them. Okay, you cannot add or subtract them. So let's begin example 1. We have noted that the frequencies has to be the same. So let's see what the frequencies are for Vs of t. Omega 1 for component 1, I'll say this is V1, and I'll say this is V2. For V1, frequency is simply omega. And for V2, frequency is omega. So they are the same, and we can proceed with the mathematical operation. So if Vs of t is 10 cos omega t plus 10 sine omega t, I'm going to convert this to polar coordinates. I'm going to write the phasor. I'm going to perform phasor transform on these. But in order to perform the phasor transform, all signals must be in cosine format. Okay, you cannot write a phasor transform from sine. And so I have to convert the sine to cosine. And converting from sine to cosine is trigonometric identity. Sine x is cos of x minus 90. So you subtract 90 degrees from the phase angle. The phase angle here, of course, is 0. It's sine omega t plus or minus 0. It's a 0 minus 90 gives you minus 90. Trigonometric identity, right? You have a right angle triangle. One of the angles is x. The other one is x minus 90. So sine x is cos of x minus 90, cosine of the other angle. So again, yes. Yeah, angular frequencies are always in radians per second. So the question being asked is about the units for angular frequency. Angular frequency is noted by omega. And so let's see, let's go back here. Yeah. So angular frequency is noted by omega. Omega is given by 2 pi f, which is also, let's see. Go back here. Okay, so omega is 2 pi f, where f is in hertz. F is in hertz, and omega is in radians per second. Let's see, the first slide right here. Good question. So again, we keep the question being asked is, why do we keep omega in radians per second and theta in degrees? We want to keep theta in degrees because we wish to perform a phasor transform where we are representing this sinusoidal waveform as a complex number. And when we represent it as a complex number, we want the phase angle information. And that's why we keep it separate. So depending on the application, there are times where we would combine omega and the phase angle together, right? Omega would be in radians per second, and then we would express the angle also in radians and combine it together. But for the purposes of, well, simple math purposes, let me put it that way, we wanted to keep the angle in degrees because we want to describe it as a vector. If we combined it together, we would not be able to use this math. So let's see here. Okay, so now here's the phasor transform. Directly write down the magnitude, which is 10, and the phase angle would be 0. That's my first quantity, V1. And the second one would be 10 with the angle of minus 90. Now, here's where I was making the point about programmable calculators. Okay, if you have a programmable calculator, go ahead and program this equation directly as is into your calculators. And let's see if your answer matches up with mine. For me, since I don't have a programmable calculator, what I'm going to do is I have to perform addition. So I want my complex numbers to be in rectangular coordinates. So I'm going to convert 10 with an angle of 0 to its rectangular coordinate. And that would be 10 plus j0. If the angle for a vector is 0, it means it's lying flat on the real axis, right? It's lying flat on the real axis. And if it's 10 with the angle of minus 90, it means it's lying directly down. It's pointing directly down. So here's 0, and here's minus 90. So minus 90 is pointing directly downwards. So length of 10. Oh, sorry, not length of 10. The real component in this case is 0 minus j10. Those are the two numbers in rectangular coordinates. And here I'm going to do this Vs of t. And now phasor transform, I'm going to use this as my handwritten symbol for the phasor. In print, it is easier to see. With handwritten stuff, you just have to come up with your own. And then the next step would be to perform the math. And so this would be 10 minus j10. And at the end, I have to go back to the time domain. That means I need to perform an inverse phasor transform. And so I'm going to convert this back into polar coordinates. So 10 minus j10 in polar coordinates would give me a magnitude of 14.14 with an angle of minus 45 degrees. And therefore, Vs of t would have a magnitude of 14.14 cos of omega t minus 45 degrees. That is my final answer. Let's take a pause while you write it all down, and I will explain. Any questions? How many of you tried to program this and obtain the right answer? No one? No idea, because I don't have that calculator. So it's, as I stated earlier, every student needs to learn this by themselves, because everyone's calculator is different. I don't have access to the exact same models that the student might have. Yes. Sure. So let's take it from the top. So we have Vs of t that is given to us as 10 cos omega t plus 10 sine omega t. we want to perform the math. We could stay in this domain and do the math, but it would be way more complicated. So what we do is we use complex number math. Now, to do complex number math, we want to express each one of these voltage sources in terms of vectors. And that transformation is known as the phasor transform. Phasor transform means you take the time domain expression, meaning a function of time, Vs of t, and represent it as a vector. That vector is known as a phasor for the source. And we can directly write down the phasor from the phase angle and the magnitude of the time domain expression. The time domain expression is 10 cos omega t. Phase angle is 0. Phasor is a vector. It needs only magnitude and angle. It does not need the value for omega. The magnitude magnitude is 10 and phase angle is 0. We directly write down the phasor or the vector for the first term as 10 angle 0. Then the second term is 10 sine omega t. We cannot do a phasor transform unless the quantity is in cosine. So we have to turn sine x into cos of x. So sine omega t becomes cos of omega t minus 90. So the phase angle was 0, sine omega t plus 0. You take 0 minus 90. And then once it's in cosine form, we can perform the phasor transform. Magnitude 10, phase angle minus 90. So far, so yes. I'll explain. Yeah. Step. All right. So that was the first step, right? First step as in transforming from sine to cosine. We good so far? Right. Yes. So question being asked is if you perform the phasor transform, if it's in sine? Well, I mean, just purely math, yes, you can transform sine and cosine back and forth. But the phasor transform itself is not going to work. Because it's a vector, it's based on the cosine. Cosine would be the opposite versus, divided by the hypotenuse. So if it's sine of the angle, it wouldn't work. Okay. So let's see. So 10 angle 0 and 10 angle minus 90. Now, this is the conversion. Again, as I stated, you could perform this math directly on your calculator. Okay, your programmable calculators, you can program 2 complex numbers in polar coordinates and it can perform the math. Okay, and again, every student needs to learn how to do this on their own. My calculator cannot do this, and so I transform it because I want to perform a addition. I want to perform a summation. So let's look at the complex numbers. What are the complex numbers? Real, imaginary, right? So far, so good. 10 angle 0. How do you plot a vector? You first find the angle, just draw an arrow, and note down the length. 0 means it's lying flat on the real axis. So my vector is right here. 0 degrees and a length of 10. That's it. 0 degrees and a length of 10. Now, this is the polar coordinates. What are the rectangular coordinates? Rectangular coordinates is the projection of the vector on the real and imaginary axis. So what is the value of this vector on the real axis? 10. Make sense? Right, so this is 10 with an angle 0. And the length of the projection on the real axis is also 10. What is the length of this vector on the imaginary axis? How tall is it on the imaginary axis? 0, because it's lying flat on the real axis. Does that make sense now? Let me use a different color. Does that make sense? Again, let's go back to this so everybody understands. This is my vector, r with an angle of theta. R is basically the magnitude of this vector, the length of the vector. And the projection of this vector on the real axis gives me the real component A, and the projection on the imaginary axis gives me the length B. So R with an angle of theta becomes A plus JB. It forms a right angle triangle, and that's why you can use trigonometric identities to perform this conversion. Does that make sense? And so let's take a look at the second quantity. Second quantity is 10 with an angle of minus 90. Minus 90, remember, if you go counterclockwise, it's a positive angle. If you go clockwise, it's a negative angle. So minus 90 means I have to go clockwise. So my vector number 2, minus 90, points straight down on the imaginary axis with a length of 10. And now if I convert that into rectangular coordinates, with an angle of minus 90, the projection of this vector on the real axis is 0. And projection of the vector on the imaginary axis is minus 10. So it becomes 0 minus J10. This will be true for every vector that has the exact same angles. Okay. If it's a vector that is, I don't know, 57.98 with an angle of minus 90, it'll always be like this. It'll become 0 minus 57.98. Make sense? Right? And graphical summation, if you sum this up, what do you get? You would get a vector that looks like this. You're adding up these two vectors together. What happens? The length is 10 on both sides is the hypotenuse of an isosceles right angle triangle. Both sides are equal. So square root of 10 square plus 10 square gives you 14.14, length of 14.14. And because both vectors magnitude are the same, it bisects the 90 degrees into exactly equal halves. And that's why you get 45 degrees. But because it's pointing down, minus 45. Okay. Let's take a pause while you think over that. Let me know if you have any questions. It's a lot of math, but again, this is simply the first example. So students, that's why I'm going slow. We need to make sure students understand everything. So above is the analytical equations and below is the graphical. Okay, any questions? Any questions from anyone? Excuse me. Shall we move to example 2? Okay. All right, example 2. Similarly, has 2. So V1 of t and V2 of t is given to us. And we are asked to find Vs of t as V1 plus V2. And I'm going to go a little faster this time. So it's 20 cos omega t minus 45 degrees plus 10 sine omega t plus 60 degrees. When you have to add or subtract two signals, first look at the frequencies. The frequencies are simply given as omega. There are no values, but in this case is the exact same. And so yes, we can proceed. To perform a phasor transform, both of them must be in cosine. The first term is in cosine, the second one is not. And so we'll perform sine x is equal to cos of x minus 90. So 20 cos omega t minus 45 remains as it is. And this becomes 10 cos of omega t minus 30 degrees. Sine x is equal to cos of x minus 90. X minus 90. Then convert it into phasor form. Simply becomes Vs. Vs is equal to magnitude of 20 with a phase angle of minus 45 and magnitude of 10 with a phase angle of minus 30. Now, again, you can perform this directly in your calculators or convert it into rectangular coordinates. When I convert this into rectangular coordinates, this becomes 14.14 minus j 14.14. And the second term becomes 8.66 minus j5. Add the real components together and the imaginary components together, and I obtain 22.8 minus j 19.14. To go back to the time domain, I need the expression in polar coordinates. So Vs transformed into polar coordinates gives me 29.77 with an angle of minus 40. And perform the inverse phasor transform. And I can write final answer. Vs of t is 29.77 cos of omega t minus 40.0125 degrees. And of course, don't forget your units. This will be volts. And then write it down, think over it. Let me know if you have any questions anywhere. We'll take a break of 5 minutes after this. So we'll wait for a couple of minutes to answer any questions, and then we'll take a break. Any questions from anyone? Okay, let's take a break, and we'll meet back at, let's say it's 10:56, 57, so maybe 11:02, 11:02. In the meantime, I'm here, so if anyone has any questions, feel free to ask.